Sure. Thank you, Marina and Dan for the invitation to give this presentation. Of course, I'll share some of the industry aspects where we use their realistic systems, and of course, we face huge challenges of using their system for validating and testing the developed approaches. But I think scientific is very powerful. We find another way to really work it out, which I'll share some very interesting ways of dealing with those lack of data or the poor models in reality. So that's why you see, for myself, I'm promoting really physics informed either state estimation or learning approaches, because for power systems, I don't really believe the power engineers are going to use the purely data driven approaches for their critical jobs. So I believe the best way that how you are going to incorporate those physics together with the data you are receiving together, and you make a better trade-off and a better decision. So the presentation for today is really the physics informed deep reinforcement learning or deep learning for power system optimization and control. So I will touch a couple of optimization and control in power system. And before that, I would like to acknowledge several of my students, PhD students. They helped me, develop many interesting works, and also some collaborators from the UNREL, Numerical, as well as some international collaborators here. And of course, I'd like to acknowledge some of the funding agencies for funding our work. So here is the outline for today's presentation. I will give a really brief background why we are using machine learning, why it is needed, right? And then I'll give a quick summary of those deep reinforcement learning algorithms, and which type of methods we have been using and why it is used for practical problems. And then we're trying to dig into the physics informed learning framework. I'll give you the holistic framework we have developed, and then elaborate on many different use cases for these applications. And then I'll share some of the thoughts and pinpoint some of the works. Probably we have to do a lot on that. So to begin with, as you all know, we have been seeing an increased penetration of stochastic renewable energy generations, especially in those inverter-based resources. They reduce the relative inertia of the box systems, and this makes really the concern of reliability and stability issues. And that means the power system dynamics may be faster and faster, and you have to take decisions under uncertainties in a quick manner, and that may cause a huge challenging for existing control or optimization approaches. And the second one is that with those reduced inertia, for example, in 2016 and 2019, those blackouts, you will see the quick frequency variations in the systems. That means if you want to prevent those changes, you have to take actions in a really quick manner, and those actions need to be fast as well as accurate. So this also causes some of the challenges for developing new technologies for that. And for those, we find the benefits of using, for example, the deep reinforcement learning to do some of the local coordinated control, which can be performing quite fast and in a near optimal manner to achieve the job. And to further with the system evolving, we are going to see a lot of uncertain DERs integrated into the distribution system, and some of the large inverter-based resources, they are participating with the accelerated services. For example, the when virtual inertia or the frequency support from the when the ERCOT systems, and how we are going to quantify those inertia and turn those inertia into the decision making process. Remember, for when inertia, this is a time horizon, and it has a lot of uncertainty there. So when you are making decisions, you have to be aware of those uncertainties and do the actions in a quick manner, right? And with all those different and diverse DERs into the systems, and then you have to coordinate with multiple timescales regarding the energy resources for reliability or security jobs under uncertainties. So these are motivating us to develop more intelligent and scalable optimization and control algorithms. And this obviously is a huge challenge for today's methodology, right? Besides those integration, we know those DRs or loads are always bringing you a lot of uncertainties. Today, we have been seeing significant challenges for getting accurate cyber physical models. I will give you more information later on, especially for distribution systems, for the secondary feeder. Even for utilities, they have no idea, about their system parameters and there. So there are huge, model uncertainties, and for the load or DR forecasting, we also have been seeing a lot of uncertainties. And then, for the forecasting uncertainty, which later I'm going to elaborate, for the MISO system, they have their huge challenges for managing some of the, uncertain forecasts, especially in those big forecasts. You have to cast them into the chance constraint optimization. But to summarize, first of all, you may have some challenges from the physical model perspective, load or DR uncertainties, inaccurate parameters, and model uncertainties. How you are going to propagate and quantify those uncertainties into your dynamic simulations. This first thing, and then how you are going to, get back with some of the sensor data for model calibration or uncertainty quantification of your physical model parameters. And for that, we have been developing some of the uncertainty quantification approaches based on those machine learning approaches that allows you to essentially quantify how those uncertain inputs would affect the partitioning dynamics. To move forward, we have also been seeing some of the good opportunities coming out from different domains, especially in the Internet of Things, that allow us to really get sufficient data for a rise of applications, right? We have been seeing a significant increase of the PMU smart meter installations and the data across different domains, where we can harness the cross-domain data to take actionable information for decision-making process. So those are the big opportunities for us, as well as the challenges for us to handle, right? So to deal with those challenges, we have been thinking about how the machine learning approaches can be effectively used to tackle those jobs. So before mentioning specifically the approaches we have developed, I'd like to give some of the high-level overview of those machine learning approaches. I know because for our audience, some of them, they are interested in the topic. They may not be the experts on this. So I would like to give a quick overview of this. So from the machine learning algorithm perspective, we have different categories, supervised learning, especially those regression techniques. We can find a lot of applications in security assessment, forecasting, as well as the classification. And for unsupervised learning, typically they are, their widely used approaches are principal component analysis, k-means, adversary networks, and these techniques can be useful for dimensionality reduction, clustering, anomaly detection, and so on. And there is another category, which is between the supervised and unsupervised learning. And this can be graph-based methods or self-learning. They can be used for both regression and prediction, or classification jobs. So in this talk, we are specifically interested in reinforcement learning or Q-learning, deep reinforcement learning approaches to help us do some of the control and optimization applications in power system. So I will specifically mention some of the applications here, including optimal power flow, the total transfer capability constraint, preventive control, OR prevention distribution system, microgrid controls, and so on. So I'll mention several applications here by developing some of the deep reinforcement learning approaches. So for reinforcement learning, there are two main categories. The one is the single agent. So you have one agent to interact with the environment continuously so that you can get the reward to train your agent policy for applications. While, for our applications, we have been developing a lot of technologies for multi-agent reinforcement learning. And this allows us to have some scalable applications, especially when you are addressing some of the large-scale systems. And for those reinforcement learning algorithms, We are specifically focusing on the policy optimization categories. Here, we have been doing some of the works in both policy graded as well as the actor critical networks. Especially for actor critical networks, we have been using the DDPG as well as the software actor critical networks extensively. So you will see many applications based on those approaches under the actor critical network framework. So to begin with, we have been developing this very interesting framework, which is called learning for optimization and control framework. And there are, based on our past experiments, we categorize it as several different subjects. The first one is the direct supervised learning. And that means you can run some of the traditional, like when you are solving the optimal power flow, you want to speed up that process, and then you use some of the solver to generate a lot of data, and then you train a deep learning algorithms so that you can directly next time predict the outcomes. That can speed up. This is the direct supervised learning. And another way that you can develop some of the deep reinforcement learning algorithms to explore the solution space and then identify the optimal control or dispatch policies. And this, you are going to transform the optimization problem into the Markov decision process that is suitable for deep reinforcement learning. And this may include, OPF, or control, preventive controls, and so on. And this can be solved by either value-based policy or off-policy deep reinforcement learning algorithms. And this allows us to really, you need to have a lot of high fidelity historic data or events so that you can do this job. But this is very challenging to satisfy in practice, right? So this is one drawbacks. And another way is really we are promoting that you have limited data, you still have very meaningful physics there, and how you are going to develop those so-called fixed informed learning for optimization. So we have been promoting a couple of ways of doing those physics informed learning. The first one is that we can replace some of the non-convex or hard to handle constraints by machine learning models. For example, for the distribution system, you may have inaccurate power flow models. This is quite true in reality. Or you may have very time-consuming dynamic constraints. For example, when you are doing the transient stability constraint OPF, and that one is really time-consuming to address. So we would like to come up with some machine learning model to replace those hard to get or time-consuming constraints while keep other constraints intact. And this would really allow us to develop a hybrid model, optimization model or control model, where you have the white box model where you have those physical constraints. It is there, and you can explain them clearly. While there are also black box models developed by machine learning algorithms, which you see here, we call them surrogate model to replace the original power flow model or the time-consuming dynamic constraint. So to solve them, we have developed a couple of methodologies. For example, with those hybrid models, you can either use heuristic optimization, because this is just searching the space, right, randomly or heuristically. So no matter it is hybrid optimization problems or a black box or white box, you can still do that. Another one, which is more analytical, is that for those black box model, you can also derive analytically their Jacobian and Hessian matrix. Once you have that, and then you can rely on the interior point optimization to solve this optimization problem. So we will show some of the examples later. Another one is the surrogate model-based deep reinforcement learning. This is quite useful when you are handling the distribution system, voltage control or other relevant problems, where you use the machine learning model to replace the inaccurate power flow model, and then you incorporate that into the decision-making process, and we use the deep reinforcement learning to address those hybrid optimization models. Another one, which we would like to mention a little bit, is that when you are having those chance constraints, it's really challenging to handle, and we are trying to use some of the Bayesian learning approaches to relax those non-convex constraint to a convex one. So this is the really the framework we have developed. So I will try to elaborate each of them by using some of the use cases or power system application problems. The first one is really on the direct learning, and this is the ACLPF problem. People are very familiar with. So I'm not going to really further elaborate on this. So what we are trying to do here is that instead of, for example, you give the inputs like load information and generation information, and then you learn the mapping relationship and get the outputs for dispatching. So, but if you directly do that, the nonlinear mapping can be quite complicated. So instead of doing that a direct mapping, we would like to divide the learning process inspired by physics to 3 different stages. So the first stage is from the load information, we trying to calculate or learn the mapping with the power flows. And then from power flows, we're trying to learn the mapping relationship with the bias voltage magnitude and angles, and with all those information together. And then we can find another mapping with the optimal solutions from the power flow aspect. So really the reason of doing that is that by dividing the learning into several stages with some of the enhancement, you significantly reduce the learning complexity. And that's why, for the learning, we're not really using a very complicated deep neural networks. We are using the extreme learning machine models. There, you can train them very fast, and it's not a complicated network. So you see at each stage, we are trying to incorporate some of the error corrections, into the module so that we can steadily improve the mapping relationship. And another very critical step we have been promoting here or doing that, for the optimal power flow, problems. Typically, for each problem, there are just a few active constraints there. So if you can identify those active constraints, and then you significantly reduce the complexity of the problem. So by using some of the clustering of the historical data, then you are able to cluster, different samples into different regions, and each region is corresponding to certain active constraints. So next time when you have new samples coming, which are new operating, conditions coming, you are able to directly identify what are those active constraints associated with that, right? And then the problem complexity has been reduced. And then based on those active constraints, and then you have the corresponding neural networks mapping relationship there. So based on that, you do the output, directly from there. So you see, we have been doing a couple of stages inspired by the physical system itself to reduce the learning complexity, so that you can achieve a good job. So here I'm showing you some of the numerical results, especially for the M6, which is a proposed method. You can see, for different scale of the systems, we can do a pretty good job while significantly speeding up, the original ACLPF algorithms. So we are losing a certain level of, accuracy, but still we can significantly, speed up the process. So this is really the benefits we are getting as compared, to other, direct learning approaches or deep neural networks. They may not be the good, in those large scale systems. Another, application is that, when you are having those, control problems for distribution system with sufficient data. Here I'm categorizing the approaches into different, amount of data. So for example, here assume you have really a massive number of historical data or operational patterns where you are trying to develop some of the policies where they can help you regulate the smart inverters or static WAG compensators in distribution system to regulate the voltage subject to the power flow constraint. And, because for distribution system, the power flow constraints may be quite inaccurate, especially when we're talking about secondary failure. So by using the, the data-driven nature of the different reinforcement learning, we can eliminate the impacts from those inaccurate physical model there, right? So that is under assumption you have sufficient data, so you don't really need to have those power flow, accurate power flow model there. So by doing that, in this data-intensive DRL approaches, we have to visit the control, architecture for these problems. As we know, there is a centralized controller where you collect all information and make the central decisions. And there can be also purely decentralized and autonomous controls, which are based on the WOWAR or WOWAT, group controls locally for each smart inverters, but they don't coordinate with each other. That means you don't have the system level optimization there. Well, another one, which we are doing here, is the centralized training, decentralized execution framework for deep reinforcement learning. And this is the multi-agent reinforcement learning. And the advantage is that during the training process, you have all the data, historic data from each individual component. But once the training is done, and then you don't need to talk with each other anymore. There's no need for communication for making decisions, while still you are achieving improved performance as compared to the purely decentralized control there. So you see here, just give you some ideas. For distribution system, you can rely some of the sensitivity-based approaches to decompose the system into a couple of voltage control regions. And for each region, you assign one agent to control that region. So that means this is really essentially a multi-agent deep reinforcement learning approach where you can do the centralized training, while once the training is done, that agent is going to just collect the local information for decision making. For example, for sub-region 1, everything is made locally decision, and you don't need to coordinate or communicate with sub-agent 2 and 3 and so on. And for network partitioning, we can based on the graph theory, or we can use the sensitivity matrix, because here we are really caring about the voltage regulation. So we can use the voltage to real active power sensitivity matrix, and then we do some certain level of clustering, and then you can divide the system into a couple of regions. For example, here, if you want to divide the system into 6 regions, and then you put this at threshold, you do clustering for the power to voltage sensitivity matrix. You can also do the similar thing for 126 bus system, and later on we will show you for the realistic distribution system, we can also divide them into different clusters, and each cluster will be assigned one agent for controlling, or regulating the voltage there. So here I'm showing for this multi-agent deep reinforcement learning approaches, and we are comparing with the centralized approach, because we are assuming everything is perfect there. While for the proposed method, this is the multi-agent, deep reinforcement learning approaches. You can see here, we are achieving closely performance with the centralized one. While you see this is a decision-making process, as I mentioned earlier, this is really one advantage where all the decision-making is here, based on the local information for each cluster. And this is really the benefits that multi-agent deep reinforcement learning is bringing for this problem. And again, this is under assumption that you have sufficient data, every type of data you have. But unfortunately, this is not realistic, right? A little bit more realistic scenario is that you have some of the good amount of data, but not really sufficient to train or deep reinforcement learning approaches. So what we have been thinking that can we use this limited number of data to come up with a surrogate model, and we allow the agent to interact with that surrogate model so that we can still train your policy and get near optimal solutions. So this is really the idea. So instead of using the physical model based on training approaches, which majority of the people is promoting, we would like to build the surrogate model, and this surrogate model is based on some of the historical data. We are using some of the Gaussian process approaches to learn the mapping relationship between the power injection to the voltage, because here we are caring about the voltage regulation. And we found that with just a very limited number of data, you can still train a surrogate model to guide the DR agent for training and getting the optimal policy for voltage regulation. So this is under a scenario you have a certain amount of data, but not really sufficient purely data-driven. But this is, another way of, mitigating that problem. Remember here, we are still doing a data-driven, but with limited number of data. Here I'm showing some example for regulating a realistic distribution system in Colorado, where we have high penetration of PVs. So we would like to have the reward function for different reinforcement learning approaches, including we would like to regulate the voltage. So we are penalizing any voltage violations, and we would also like to minimize the curtailment from the PV generations. So we find that for some particular regions, the voltage regulation, they may be slightly over the the limit, for example 0.9 to 1.05. So we slightly relax the voltage violation penalty there a little bit by adopting a certain residual factors there, and we found this is working very nicely by doing that. So here, this is the realistic system we have been testing. And of course, for this realistic system, you don't have sufficient data to train your deep reinforcement learning. And that's why we come up with that surrogate model to help us with this task. And this is the 759 nodes with 77 PVs. And this is about 80% penetration for the whole distribution feeder here. And this is the testing of the surrogate model, because now we are using the surrogate model to train our policy, right? Instead of the perfect physical model you're having. So as you can see, with those advanced reward function, we relax the penalty or threshold there, and then we only have at most 2 load of violations. That means 2 loads have a little bit voltage violation issues across the 759 loads. And we also show that with those different reward functions, we can do a pretty good job of regulating the voltage within their operating limits, with just really a few number of loads having voltage violation problems. And actually, we've also extended this idea to the optimal or community microgrid control, especially this is under break order 2x4. Some of the community microgrid, they may participate with the electricity market, but each energy hub here or each microgrid there, they are only communicating with the retail agent, which is a central agent here, and he has no knowledge about others. So this is really a decision making under uncertainties, right? So to come up or to address this problem, we would like to come up with a surrogate model. Again, we are getting all the available information together. For example, the central agent retail energy prices, renewable energy inputs, outputs, and demand. And then we train that agent. And later on, we are going to make the decision, for example, for energy hub 4. And then, for each individual hub, we are going to use the deep reinforcement learning to get the policy for that energy management for energy hub 4. So instead of directly interacting with all other energy hubs, we are interacting now with the surrogate model, and by interacting with the surrogate model, we come up with the optimal policy under that. And of course, this is under uncertainties. So we train the policy, and then we found that by doing this, even under large uncertainties, we are able to achieve satisfactory benefits for those energy communities. So this is really another idea by extending the surrogate model idea, together with the deep reinforcement learning for making decisions under uncertainties. So for more details, you guys can feel free to look at the paper we published there. And another more, or most of the cases for utilities that for distribution system, you only have a very limited number of data, really limited. And it may not be really sufficient for you to even train a surrogate model there. And you still have a model, those models are not that accurate, right? For distribution feeder buffalo model, you're not having an accurate model, but still it is useful. So we're asking ourselves, so this is a realistic scenario for most of the utilities, how we address that by really training the deep reinforcement learning agent to achieve the task. So we think about how about the multi-fidelity learning. So the idea is that you have a limited number of historical data, really limited, and you still have the physical model, calculations. And for this physical model, you can generate, as much data as you can, but they have, lower fidelity or lower accuracy as compared to the measurements. So by fusing the lower fidelity data together with the high fidelity, limited high fidelity data, can we come up with a surrogate model that can reference the power injection mapping to the voltage? So this is really the key idea. And essentially, we have some, from the computer science, domain, they have developed some very interesting approaches, which is the multi-fidelity learning. So from the low fidelity learning, you can have a mapping relationship, and for high fidelity data, you can have a mapping relationship there. So we are making the assumption that there is a certain relationship between the low fidelity data as well as the high fidelity data. And of course, this is true, right? Because you are, no matter you are high fidelity or low fidelity data, you are observing the physical response. So by using these correlations between high fidelity and low fidelity data, we are able to train our two neural networks. So for high fidelity data, you have that neural networks. For low fidelity data, you have another neural networks. So during when you are training a high fidelity data model, there you are using those high fidelity data to correct their network parameters for those low fidelity based neural network model. So this is the main ideas by fusing a few high fidelity data into the low fidelity models so that you can improve the low fidelity projections. And we find that this is really powerful. And again, we are using that realistic filter model. We have really a limited number of data. For example, here we have just 1,000 data, historic data. And from the power flow model, you simulated 100K data. And then from the voltage prediction perspective, we can achieve 10 power minus 4 absolute error accuracy. While if you have a perfect model, or you have almost perfect model, there the predictions 10 power minus 4. So that means with really a limited number of data together with the inaccurate physical model, you can do the similar performance with very good power system model. So that means with this surrogate model, you can still train your DRL policy and get the control strategies to manage the problem, right? So here we tested on this scenario again, for the same systems, we slightly, actually we don't modify the reward we have been using before. So we adopt the previous reward and we do the testing. And you find that here the yellow one here, this is the real. That means you are using a perfect physical model to train the policy, while the blue there, is the surrogate model we are training. So most of the time we are achieving even better performance as compared to using the perfect model. And there is one very interesting phenomenon here is that when you have a sudden or really unforeseen scenarios for for the PV coefficient, here is the PV shape, and then you may have some problems for regulating the voltages. And actually in today's presentation, I didn't show another approaches. We have already addressed this problem by adopting some of the auto tuning for deep reinforcement learning approaches. We don't have this issue. So in general, by using those surrogate model together with multi-fidelity learning, we can do a pretty good job of regulating the voltages while minimizing the PV curtailment. So this is the some of the curves for voltage regulation, and typically we only have approximately 2 loads that may have some voltage violation issues, and this is verified from the physical system grid aspects. They always show up some of the voltage issues there. It's really their system design problem. It's not the control algorithms. We also show the scalability of this approach for larger system like 3,436 loads. With here we are putting 6 utility scale PVs, and we demonstrate that even with the larger scale distribution feeders, we are able to achieve similar performances as compared to the centralized optimization-based approaches. So this is pretty good. From sufficient data to moderate data to very limited data, we are able to achieve the expected outcomes under this physics informed deep reinforcement learning framework. So, and another major category, as I mentioned earlier, is the hybrid or white box plus black box learning and control problems. So here I'm showing this is the total transfer capability problem. That means when you have some contingencies, there might be transfer limits for certain transmission lines, the critical transmission line corridors. And then for doing that, you have to incorporate, if you want to come up with some of the generator dispatch policies, you have to include the strength and stability constraint. Again, that means for each evaluation, when you are running the security constraint OPF, you have to run a time domain simulation for checking if the system is satisfying the stability or not, right? So if this is a large scale system, it's huge time, demanding. You cannot achieve, for example, 50 minutes or even half an hour dispatch, rules there. So our idea is that since this one is really time consuming, why not? We just come up with a deep learning model to allow you to predict, the system trend and stability. So that every time you give me the initial condition, I can predict if the system is stable or not. And then you run your security constraint ACOPF. So this is the idea. So, by using the deep learning surrogate model, of course, it comes with another problem, that this is a black box model, right? It is not the way that the traditional optimization softwares or algorithms they can handle. So to deal with that, we are using a couple of different approaches. The first obvious or straightforward approach is that why not you just use some of the heuristic optimization based approaches, because again you can generate a lot of data and then you search on the space and then you can solve that optimization problem. But we can only get suboptimal or local optimal solution out of it under that hybrid optimization problem. We demonstrate that it is working nicely for us to redispatch the generation so that we can maintain the system stability under that certain scenarios. So this is using the heuristic optimization. We're also trying to come up with some analytical solutions. Again, this is the similar problem for the TDC control. You are trying to minimize the dispatch cost of the generations, either to try traditional generations or wind or battery energy storage. But still, for that, security constraint dispatch problems, you have to include those strength and stability constraints there. So we are also trying to use another surrogate model. And the point here, different from the previous one, is that we would like to incorporate really this one into the optimization module. And we would like to use actually the interior point optimization problems. So the challenge is that for interior point optimization for the white box, you can easily calculate their Jacobi and Hessian, while for this black box surrogate model, you have to derive analytically the Jacobi and Hessian matrix for that. So of course, you can, based on the deep numeric surrogate model, you can derive, actually all details can be shown in this paper. So we derive the analytical Jacobi matrix as well as the Hessian matrix for that black box surrogate model. So with all those, you can feel free to use the interior optimization methods to address actually to solve this problem and come up with the dispatch policy. So really, the interesting point here is that by doing this repeated calculation of TDC prediction, as well as using the sensitivities to guide the dispatch of those generations, you are able to control the system and maintain the the system stability. So this is really a very interesting work, we have been doing by, analytically calculating the black box model, Hessian as well as the Jacobi's. Especially for the Jacobi's, you are able to identify the critical, tie lines which are affecting the system stability. So from that case, you redispatch your generations, either wind generators, energy storage, as well as the traditional synchronous generators to maintain the system, transfer capability or enhance that transfer capability within that framework. And the last work, we are trying to do is that from the learning aspect, if you have some chance constraints, for example, here, this is one realistic scenario in MISO. They have a large, predicting errors for their, they had prediction there. So that means for such a large predicting error, obviously some of the security constraints you set there, they may be violated, right? So that means, for the ACOPF problems, there are certainly, if you're considering the uncertainties from the DRs or loads, and then there can be some probabilities of violating them. So the question is that for those chance constraint problems, it's non-convex, and also, for chance constraint, you don't really have the accurate probability distribution for that, right? Which is really challenge there. So to deal with that, we come up with the Gaussian process model, based on historical data, and then we're trying to learn the mapping relationship, for that chance constraint. And thanks to that Gaussian process model, which is the Bayesian learning, you are able to characterize the probability of, violating that constraint, where you can assess the risk. And another nice property for Gaussian process model is that this is a nearly analytical model there. It is a white box model. And by doing that, you can really relax the original non-convex chance constraints into a convex, convex chance, constraint there with certain probability characterization. So with this reformulation, you are able to use some off-the-shelf solvers to get the results. And we show that with those approaches, you are able to really regulate or dispatch the generations while maintaining those chance constraints within. For example, here we are putting 5% violation probability. We can certainly do that, as well as achieving some certain dispatch benefits. So this is another work we have done in the past, by using some of the reformulation from the learning aspect, turning some of the very difficult, chance constraints into a more and easily handled chance constraint, for handling. So to conclude today's talk, really here we are really promoting integrating the inherent physical information together with some of the limit data for learning and control. And one advantage is that once you incorporate those physical information, you don't need to have the massive requirement of the data, historical data, which is really the benefits we can get. And also, physically informed deep brain learning, it has higher interpretability as compared to purely data-driven approaches. As you see in the previous example there, with the learning, we calculated the Jacobi and Hessian, right? Especially in Jacobi, the sensitivity, you can identify those critical tie lines. And this is really benefited from the physics. And of course, to use those approaches, you really need to specify the data and computational requirements for practical applications, especially in the data, the amount and variety of the data and how it is computational efficient to handle different applications, because there are different time scales, right, for the problems. And also when you are handling those practical applications, there are always many challenges, especially from the data quality perspective. There are frequently bad data, non-synchronization of the data, missing data, and so on. And we also need to address the interpretability of the deep reinforcement learning approaches, because you really need to get those information, how this is going to give you the expected results. And we also need to respect the physical constraints and collaborating with power industry, especially utility, using their system and data for validating and testing. So I think that's pretty much I have for today. I think we are on the right track, right, Marina? So I'm happy to answer any questions you guys may have.
Thank you, Junbo. This was great. Thank you so much. So a lot of questions. I guess there are some questions in the chat. And maybe we should start with Amar. Amar, you want to ask your question?
Can you hear me, Maria?
Yes, yes.
A very nice talk, Junbo. Very interesting ideas. I was just wondering if any of the codes are available open source. I'm seeing your GitHub. I could not find them there.
Oh, okay. Yeah, so many of these works are still ongoing, right? I think if we done this framework, very to a certain degree, and we will be very happy to share some of the codes there, because this is really promoting the open access of the data so that people can test and validate. I think this is really a benefit. We are really certainly promoting that.
Okay, the related question is really, where do you get the data from? Is there under NDA, or how are you dealing with that?
Yeah, it's under the NDA.
Okay,
because,
so
thanks to our relationship with the utility, right? So
yes,
we don't have that concern for getting their system data, historical.
So how do you publish these using NDA data?
For this, you cannot disclose their specific, distribution system, for example, parameters, the historical SCADA data and so on. You cannot disclose. And that's why even you see in my presentation, I'm using very high level figure, especially for some of the realistic data, right? You just see that, but actually it does not tell you too much information there. For example, here, but that is a realistic system. Right?
Okay, so we can still publish qualitative results, but I think, Amar, I don't think it will ever come to here is the set of data and here is the code and you can reproduce this data, because data you cannot get. So you can maybe get the code, open access, and then create your own data and test. Is that correct, Junbo?
Yeah, that's correct. Or we can open access some of the algorithm tested on the IEEE benchmark system. Like
I think that would be great. Yeah, I think sharing the confidential data, I think, is dangerous for everyone. So
right.
Yeah. So yeah, as long as it's a test system, yeah, it's fine. Thank you.
So I want to ask one question, which actually it's a sort of elephant in the room in this area. So we have not done this in power systems either, but utilities think it's true. Anything that you put on the system, in particular software, it should be provable, right? If you do that, I know that it's going to happen, right? So machine learning tools are generally not provable. And so I think one big area, I had a question which relates to that, like what are the open R&D questions? And I send you personally, Junbo, in your emails, you'll see several ideas on this, but basically the question is, how do we combine physics-based models and machine learning so we have some probable claims for, like, if we do this, we are going to meet this reliability standard and stuff like that. I've been working a lot on, even before machine learning, how is ICOPF provable? Well, it's not provable. So I think as we try to innovate here with database, new data and so forth, I think we are going to be hitting this question more and more in power systems. We as a community, and I'm getting older here, so just want to share the idea with you guys younger, I think is that somehow we have to deal with this transition in which, because the systems were operated in a predictable way, you didn't have to have provable performance, you had best practices and so forth. Now we are moving much more into new operations, and everybody would like to know if the system will fall apart and if you do something. So I personally think that that's really one of the biggest challenges to us as we go, but I'm interested in your comments to that.
Yeah, first of all, I'd like to elaborate on that, Marina. For example, here in this particular example, for example, we are now working with Eversource Energy, right? So they have huge challenging for visibility of the distribution system operation or feeders, and they have really limited number of SCADA data in their system, really limited. And they, of course, they have a billing history and so on, some of the event logs and so on, but still their distribution feeder is not that accurate. So I come up with this idea, multi-fidelity learning to them. I say, okay, just give me whatever you have, very limited number of data. Give me the Buffalo models there, and then let me do some of the validation. So later on, I think last month, I give them a presentation and showing that even with those limited number of data as well as the poor distribution feeder, we are still able to give them very satisfactory outcomes for them to take a look at the visibility. So they are convinced that some of those technologies, they are playing a major role because they don't have any tool to handle that visibility.
That is absolutely great. Mm-hmm. So then why don't you take over the next questions and ask mm-hmm. people? And, yeah.
Sure. So there's another question from the chat. Ramesh, maybe you want to speak for yourself? All right, so Ramesh just asked, like conventional grids relays algorithms will work for the IBR-rich grids. We may have to rewrite suitable algorithms for the relay IBR-rich grids. Is that what do you think? Junbo?
Yeah, this is another very interesting work, especially when we're talking about the high penetration IBR grid. The coordination of protection relays is really a huge challenge, right? So, very interesting. I have one student, he's a part-time student, he is working in the industry, and he is very interested in relay coordinated settings, and tell him, you can use machine learning approaches to learn the settings of those relays under different faults or different operating conditions, so that, later on when you are having certain problems, it can directly give you those coordinated relay settings instead of manually tuning and so on. So I strongly believe, since this is a challenging problem for the industry, they don't have good solutions for that. And still machine learning can help you at least provide you some of the hints or some prior knowledge where you can judge on those machine learning outcomes to set your relay coordinations there. So at least I see this is quite beneficial for them, especially for those problems they have no, or they don't have good ideas for solving.
Thank you, Dr. Zhao. This is Ramesh Suryavanshi with you. Can you hear me loud and clear?
Yep.
Yeah, thanks a lot for the explanation. I think we need to do a lot of challenging work here to resolve this issue. We're going to face a lot of problems on IBR-rich grids. Mm-hmm.
Yeah, great. Especially you mentioned this protection relay coordination. Certainly, this is a huge challenge. I believe machine learning can help you to a certain degree.
Thank you,
sure.
Dr. Zhao.
All right, so next question, Rebecca, maybe you can speak out your question.
Sure, hi, thank you so much for the great talk. It was really great to see the different technologies and the different approaches that you're taking to solving different problems. I just wanted to come back to your earlier comment on where to this kind of utility distribution system approach, machine learning plays a big role because there isn't a lot of data available. And so you can get a lot of performance that you might not have had before. But what about in transmission, where historically we do have a lot of data and we know the system parameters, we might know them quite well. Where do you think the role of machine learning is there? And perhaps kind of looking at in like OPF, security constrained unit commitment and things like that, beyond the non-convexity of the problem?
Yeah, really, I think for machine learning here, there are two huge benefits we can get. The first one is speeding up the solution of the problem, right? Especially from large scale ACOPF this type of problem with machine learning, you can significantly speed up the calculation speed. And another big advantage is really handling those uncertainties. Some of the uncertainties, you may not have an accurate probability distribution associated with that. While for machine learning, they are going to directly get those mapping relationship between your uncertain inputs to the outputs. For example, you can use some of the Bayesian learning approaches to handle this uncertainty. So at least from in the transmission system, there I see those two strong benefits in enhancing the computational efficiency as well as handling those uncertainties. Another thing is that when you are handling those control problems, again, those high penetration of IBR systems, the control interactions between each component can be quite complicated. It's really challenging to design those controllers for that. And I strongly believe the deep reinforcement learning approaches, they can do a pretty good job of handling those quite complicated control problems. So at least from my personal opinion, even with very good amount of data in the transmission system, you can still benefit from the machine learning approaches. And of course, those benefits can depend on different applications you are working on. But in general, those are three big benefits I'm thinking of.
Thank you. Could I just squeeze in a really quick follow-up? I'm wondering, how do we then convince kind of operators and system operators that machine learning is a tool to look at where there's a lot of hesitancy, where the state of art has worked quite well? I mean, when you say uncertainty with renewables, that's kind of an obvious connection. But what about some of the other approaches?
Yep. So, in practice, probably you can put the machine learning based approaches as in parallel operation as compared to your existing tools, right? So, if you see something not working in your traditional approaches, you can take a look at your machine learning algorithm and see if they are making sense or not, because you have those experiences, and you start to build those trust to those machine learning algorithms, right? And in the meanwhile, you in a normal operation, you see, oh, your traditional method is getting your results and machine learning is giving the results. You see, oh, they are quite close. So based on the continuous double verification from each other, you can build those confidence on trusting those machine learning applications. So of course, it takes a long process from the operator to trust those outcomes. But from the academia research perspective, we have to develop those technologies. When one day they are requesting that, it is already there, right?
Right. So, Vladimir, I would like to ask some questions. So, yeah, go ahead.
Yes. All right. Thank you very much, Junbo. Thank you very much for this lovely presentation. I always like and enjoy your presentations whenever I can. Let me ask you a bit general question related to machine learning and artificial intelligence. In your opinion, to which extent understanding of the physical process and the applications and the sense of the whole network, in our case, generation, transmission, distribution, utilization, how important in designing a practical, robust, useful, applicable machine learning based application is understanding of the physical process as such? Some students say, no, we don't need to understand physical process. They just jump into a topic and start designing something. And then I ask them a basic question, they are not very confident. But still somehow these applications are working. But what's your own opinion, please?
Yeah, very nice discussion here. At the very beginning of the presentation, I say clearly to the audience that I'm a guy promoting incorporating the physics into the learning process, because I strongly believe the system operators, they are not going to trust the results purely from data-driven, because from the data-driven approaches, there is a lack of interpretability, which is quite essential for them. They have been very familiar with the system. Whenever action they take, they are expecting something. While for the machine learning models, if those data are following their training patterns, and then it's fine. They can give you the results you expected. While if they're out of sample, that means you predict something, but those are not they are looking for. So they will have some doubts, especially for those security, critical missions, right? So what I would, prefer is that why not incorporate those physical understandings into your, machine learning design? Especially, for example, you can add those constraints or regularizations in your machine learning models, where you can, enforce your learning agent to satisfy those physical constraints, because those are hard. You must satisfy whenever you do. And this could significantly improve the interpretability of the decision-making process you are doing, right? So you must give certain level of explainability to the operators. They know, okay, whenever I take this action, it's going to happen in that direction. So he's going to predict something by himself based on the past experiences. And it's really essential that you incorporate those physics inside there for interpretability. This is the first thing. The second thing, that for many power system applications, especially for transmission systems, we are talking about transient stability prediction and so on. In reality, you don't have those, massive faults or events in the history, or even you have them, but the system has been evolving for many, many years, and it has been huge changes there. So you cannot really use them. So the good advantage for adding physics is that the physical model is not perfect. It's fine. At least they give you the majority of the scenarios, they are working properly. Otherwise, you are going to have a lot of major blackouts here and there, right? So the system, if there is operating, that means majority of the scenarios, they are doing a good job. So, by using those knowledges together with some very high fidelity data, and then you are compensating with each other. So that means you are using the data to help your model to improve either from parameters or understanding of the problems. And in that way, you have significantly reduced the requirement for the data for training the machine learning algorithms, which I showed specifically for this example here in my screen. I was working with a utility, and they told me, this is all the data I have. Right? I said, come on, this is what we have. Yes, this is our reality, but we are looking for some solutions for visibility. And I come up with this solution. I say, okay, give me the data and give me the model whenever it's poor or not poor or whatever. And then I come up with some solution. I say, at least we can give you some satisfactory predictions. And it's better than nothing, because in the past, they don't have anything there. They don't know what happened there. But now I can give you some hints, and they are very happy with that. So you see, incorporating those models, the physical model, whether they are accurate or inaccurate, they can still help you. And this reduce the data requirements, right? So I think those are the two major issues we need to really achieve using this physical laws. Increase the interpretability, which is on the other hand increasing the security of the decision-making process. Another one is using those limited data as well as the physical laws. You can train a good machine learning models without too many data.
Yes. Thank you very much, Junbo. I fully agree with you. Thank you.
Sure.
So Junbo, maybe I have to ask my question,
Sure.
which could be a hard one for you. So I remember that you talk about something like using the machine learning to learn the convexification of some non-convex problem. So my specific question is that how do you know that your machine learning model can approximate the convexification, because to testify whether a region is convex, that problem itself is really hard, right? And yeah.
So that means you have to impose some of the constraints during the learning process. For example, for the Gaussian process, it is an exponential function there, right? Which is convex, right? So you can, from the impression, or representation of that algorithm perspective, this is a convex function. And then, from the input domain there, if you add some constraint there, and then you can make sure the learned problem is still convex. So of course you need to add some regression there so that they are follow the convex pattern.
I see. And then how could you verify that the learned convex-fied problem has the, shall we say, the exact solution as the non-convex-fied original problem?
This you cannot guarantee because you are approximating, right? You are trying to reduce the complexity of the problem, and that means you are going to lose some of the accuracy. But in the meanwhile, you have problem that is easy to be solved. So there's a trade-off.
I see. So that means you probably don't have any guarantees on the exactness of the solution.
No, this is impossible. I don't think it's possible.
I see. Yeah. Thank you so much for
it's something like you may get a little bit more need to conservative results, but still, they are under the feasible region, and then you achieve those, benefits of speeding up or, solving the problem easily and so on, right? So you are achieving other benefits.
Right, that's kind of a compromise that we have to make.
Sure.
Right, so
there's no free meal, right?
Right. So any other questions from the guests? All right, so I think that's for today, and thank you everyone for joining today's seminar, and we'll see you next week.
Yep. Thank you, Dan and Marina.
Yeah.
Take care, guys.
Take care. Bye.
Bye.